fact that if you use Arbitrum's native bridge, you have to wait a full week to use your funds. And waiting a week, I think, is kind of like not even Web 2, but like pre-web and the death of UX. So why does it matter so much? For that, what I'm going to do is analyze the life cycle of a packet. Go down the stack into what happens when actually data is transferred from one chain to another chain. For all intents and purposes, a data transfer is an asset transfer too. Because in the end, like sending funds from one chain to another chain is basically telling the destination, hey, I'm sending you this many funds. So we're really looking to just transmit bytes from one side to the other. So at the moment, if we kind of look at the stack that we have right now with Union Testnet 8, this is approximately what we spent our time on in the process for getting a transfer from one chain to the other chain. We wait a long time for a specific chain to finalize. In the case of, for example, Berachain, we only wait 1 second. In the case of Arbitrum, we wait their soft finality, which is a full hour. In that process, we're like not really doing anything at all, but actually consumes a large portion of protocol time. Then we have proof generation. That's something that we really heavily optimized. Previously, competitors would spend minutes doing proof generation. And if your finalization time is only like 1 second, then a minute of proof generation time is quite a lot. In our case, we spend about 7 seconds generating a proof. The next part is RPC latency. Because we're all working like peer-to-peer networks, it takes a while for a block to propagate over the peer-to-peer network and arrive at an RPC. And this is noticeable with really fast chains. So if you have these chains that produce a block every 200 milliseconds, then the RPC latency might be 3 to 4 seconds for the whole network. So it takes a while for actually like our relayer to observe that stuff going on. And the same way when you like submit a transaction somewhere, like there's a bit of wait time that technically could be 0 if we just had like better network IO infrastructure everywhere, if like the API pipelines would be better. So RPC latency, transaction inclusion, that's kind of out of our control, but we see it improve overall, and you can improve it with better integration in building pipelines. So first, the lifecycle of a packet. User submits a transfer, and they interact with the source chain. So that's a chain where they have their funds, and they want to move their funds somewhere else. There's still a bit of like RPC latency here, and transaction inclusion latency, because the user has to interact with that source chain. Our relayer is continuously monitoring the source chain, and if it sees those transactions, will generate a ZKP, submit that on the destination side, and afterwards submit a packet. This is like a perfectly beautiful protocol where it's like obviously simple. This all works fabulously well on paper, but if you actually run this in production, you start to realize that you have that dreaded finalization barrier, where indeed between the time that the user submits their transaction, the relayer cannot mathematically generate the ZKP yet. The validators haven't signed the blocks yet, or according to the consensus protocol, there's something else that you need to wait for. And like I said, this can be 1 second, which is fine, and then you have a really nice fast system, or this can be a week, and then this is absolutely terrible. So we asked ourselves, like, what are ways that we can actually do this better? How can we reduce that finalization barrier? Because that really makes the UX a lot better for our end users. The first question you can ask yourself is, do we just improve chains specifically? Yes, that is like ideally the objective, and Ethereum has now announced a potential roadmap to have faster finalization. Ideally, we would see it like now. The planned timeline is maybe in the next 5 years. And given that they overshot their timeline for staking as well by about 5 years, let's assume it's going to take like 10 years actually for us to see faster finalization times on Ethereum. So you need something else to improve this. Can we do better? We can actually look at other intro protocols or other ways to basically do this faster. And right now the fastest way to do this is what we like to call intent-based bridging. I just did a panel about like generalized intents. I don't really like the term intent-based bridging. I prefer to call it open filling. Instead of the union smart contracts fulfilling an order for the user, we just allow anyone to fulfill that order. And what that effectively does is it moves risks away from the smart contracts to some other party. Like a really nice solution. Union doesn't take the risk at all, someone else does. The good thing is an off-chain party is much better capable of handling risk because they can run arbitrary amounts of off-chain compute, they can interact with Binance, with fast price feeds. So the risk that they take by doing a filling order isn't as great as it is for the smart contracts. When we do that, ideally we want to actually have that be integrated in the core protocol that I just showed. Instead of a new layer being on top of, built on top of Union, we're looking to actually speed up the core protocol. And one big realization that we had is even though you mathematically cannot pre-compute the ZKP and inclusion proofs and get them to be submitted on-chain, an off-chain party ahead of time will know what they look like already. And so actually they can provide a payload that already has proof data associated with it. And even though the smart contract cannot verify it yet, once that finalization barrier actually passes, those proofs will all be valid. So in the meantime, we actually have that off-chain party calculate what the proof will be, submit the packet, and fund the costs that are necessary to fulfill the user transfer. This, to be honest, is all basically like solver bro technology, where basically you just decide, hey, we're going to offload this complexity to parties like Aori or Propeller Heads, and they're going to run some big off-chain infra. But it does work really well. And actually in practice, when we build out bots that do this work, the bots turn out to not be that complex. This model actually works very nicely. So what you effectively get, and this image looks very similar to the previous one, but in the timeline itself, in the sequence diagram, time goes from top to bottom. What you can actually see is that the relayer is capable of submitting packets before it generates the proof itself. Now, we obviously love IBC, and so we cleverly hijack IBC in the system. IBC always sends an acknowledgement back. So when a transfer is submitted on the one side, it sends a packet back to the source side to tell the source side actually the transfer was completed. Now, normally this acknowledgement contains no data whatsoever. It truly is just kind of a little ping, a single byte to indicate the transfer succeeded. What we actually do is we overload the acknowledgement. In the acknowledgement itself, we put data on which solver actually fulfilled the order. And that way the solver basically still uses the ZKP-based route to get their funds back, but the user gets to have their transfer be fulfilled intent-wise. And that's what I like to call solving the immediate need, which is a user has a UI in front of them and they want to be done with the bridging operation in like 3 seconds, and the slower need, where a solver is capable of waiting for a longer amount of time. Now, a solver still wants like the acknowledgement to be fast, because a solver has, let's say, 10 million in total spread over 10 different chains, and it wants to make revenue of this. So the more often it can use that 10 million, the more often it can cycle it, the more it makes. The cool thing is, because Union is so fast, actually the system is incredibly efficient for solvers as well. And so they can cycle their capital much more often, or more effectively, need less capital to serve users. And that's great, because right now solvers are very well capitalized. It's kind of hard to do solving at scale as a small user. But with systems like this, you can actually do it with less capital. So why do I think this is actually cooler than building like a full stack on top of Union that does separate intents? First of all, if you look at the code, it's transparent. And by that, what I mean is developers still write code assuming it's a regular packet that arrives. They do need to opt in on this, and they do need to be aware that the packet that they get could contain data that's invalid. So this works extremely well if you're doing cross-chain transfers or DEX swaps, for example, where the solver provides the funds. Because it doesn't make sense for a solver to provide invalid data, because they would lose the funds themselves. User would, to be honest, look out if a solver makes a mistake and provides invalid data, because they would get their money twice. But it's not a separate protocol that people need to use. So really you stay within kind of that same network I/O stack that IBC provides you. And what you naturally see is just that some transfers will go faster than others, because those transfers have a higher fee associated with them. And so as a user, if you basically move the slide forward, pay a higher fee, things just go faster. The piggybacking, like I mentioned, basically we don't add additional messages. So at scale, this system actually does exactly the same amount of packet transfers as regular IBC does. So total gas cost for the entirety of the Union protocol stays exactly the same. It's actually slightly smaller with the intent-based route, but we don't really have like additional gossiping or additional packets to do bookkeeping. And I think that's extremely important if you want to actually build an intro protocol that can scale extremely efficiently. And moreover, right now, if you look at intent-based bridges, they usually use an oracle to pay back the solver. UMA is the biggest one that's used right now, and UMA on the top of my head has a 1-hour latency, which means that a user might get their funds 3 seconds later, but the solver has to wait a full hour to actually get their funds back. So in our current setup, we're basically the same performance as UMA has for Arbitrum. But for Ethereum, for example, we're much faster, about 4 times faster. So a solver only needs a quarter of the capital to serve the same amount of users over Union. As we see, like, Ethereum, Arbitrum, and other slow finalization ecosystem speed up, Union naturally benefits from this. So as underlying infra actually gets faster, we don't need to change the protocol at all. We will naturally become faster as well. So this is a bit of a nerd snipe, so I hope that this doesn't fly off your head or that you guys find this interesting. But I'm going to dive a little bit into like some of the cool stuff we had to build to make this work. We've previously like published a lot of research on this, and I think that for most the research might seem to like not fit together, like cool tech, some new stuff, but why did we actually invest time in it? And I hope this makes it a bit clearer. So one big thing for those familiar with IBC is IBC leverages sequence numbers. Every single packet has a number associated with it, and the next packet has the previous number plus one. Now, this doesn't work very well for intent-based bridging, because the whole point is that we want to be able to compute everything off-chain. And the assignment of that number always happens on the source chain. So that was the first thing we got rid of. We actually, under the hood in Union, we still support sequence numbers, but internally the protocol actually does hash addressing. A really cool benefit is it immediately made the stack 10% cheaper, gas cost-wise. Because on the EVM side, we avoid actually hitting one storage slot. So that was a good benefit. Another benefit is when you work with parallel blockchains, having that single sequence number is kind of like a global mutex. It prevents parallelization of the bridge transactions and makes all of their costs slightly higher because you create a hotspot. So for Aptos, Sui, Movement, Solana, the gas cost slightly increases, and if you're lucky and thousands of users want to use the same bridge, at the same time, then actually like a hotspot becomes very significant. By doing that content-based addressing, you don't have hotspots at all anymore either. So the contracts became like a lot less stateful and to be honest, easier to implement. Another thing we built was state lenses. That goes really deep into IBC, but everyone right now uses packet forward middleware. Packet forward middleware has the same issue with sequence numbers, and actually it transfers one sequence number into another sequence number, which makes the whole intent-based route completely impossible to do, because you will always need to hit the intermediate chain to do intents, even if you want to hit the destination. Instead, what we do is a light client of light client technology. So basically on the destination side, we access intermediate light client states of chains. That has a really good benefit because all of these hashes stay exactly the same. So you get kind of a recursive storage proof, and with that recursive storage proof, you can prove an arbitrary path. And so this, although it's probably like the most technical change we made to IBC and the Union protocol, actually was like incredibly critical to doing the intent-based bridging. Without that, that would be completely impossible. The transparent entry points, I've named it 3 times right now, but those were actually really trivial to do. It turned out to be like 3 lines of extra code to make all of this work for developers using us. And finally, we built our relayer from scratch to be plugin based. And the whole reason we actually did it plugin based wasn't to make it easier for us to add new chains, because we control the source code anyway. Like we can add new chains whenever we want. It's so that if you already are doing MEV, or serving other intent-based protocols, you can combine this order flow much more easily. You can basically be doing a cross-bridging and union bridging through the same software. And the cool thing about our relayer is it'll batch these transactions together too. So it'll basically figure out everything that has to go into Ethereum, no matter what you're doing in the sandwich tags, DEX trades, whatever order flow you've got, and combine all of those into single like big batch transactions to settle atomically on Ethereum. So it has a good benefit to be extremely composable with kind of this wider off-chain ecosystem. I find that stuff really cool. I actually really love the boundary between blockchain and off-chain to kind of see how stuff then still works really well. And that's where I often see other companies fail, to be honest. Like it works on the smart contracts, but then they spend 6 months on the integration side to actually get stuff to compose. Now, once you're in this state, it was kind of like the V0 of our intent-based bridge, we started to get delusional, right? Like if actually you make this protocol extremely flexible, could you push it even further? Actually, the acknowledgement that repays a solver can be sent optimistically too by an intent. And so a solver can actually use this if it wants to rebalance itself out against another solver, right? So as long as someone else is willing to fund the capital, it can handle the acknowledgement and get the funds on the other side, and basically perform a swap, right? So by combining these like packet transfers and acknowledgements, you actually have a rudimentary cross-chain DEX setup. The protocol doesn't like need this. This is an optimization that solvers can just perform, right? Cleverly doing this to basically spend less gas overall. And you can just keep doing this all the way down, actually. Like you can keep doing packets, acknowledgements, all intent-based. And all the way in the end, all the way down, you then need like one ZKP to basically settle this almost payment channel that you have created. I suspect this will take a while to actually like appear in the wild, but it's a really cool like nerd snap side effect of building a protocol that at its core is really flexible. Now, can this become even better overall? Yes. I know the slides. Sorry guys, I made this last night midnight, so I'd try to remember what I meant here. I think I'm just literally retelling what I just told. Oh, no, actually, yeah, this is the thing. So I kind of already talked about like where do we spend time waiting for stuff. We have this like transaction inclusion latency, RPC latency, which if you look at our current testnet with like 1 second block time chains, occupies about 6 seconds of total time out of a 20-second like transfer duration. That's how much we spend like waiting on like Alchemy to put it in a mempool, to put the transaction for the user on chain. That's how long it takes like our relayer, once it's like constantly querying multiple RPC nodes to actually see the block for the very first time. Now that we have this intent-based model, actually what we can do is something far cooler, which is, I don't think you can see it very clearly here, if a relayer knows that a user is going to submit a transfer, and it's really sure that the user is going to do it. For example, I don't know, the relayer actually is a wallet, and so it has like really first access to that user transfer. It is actually perfectly free to already put it on the destination chain before it gets included on the source chain at all. Now this is quite risky for the relayer because what if a user is sending out like 2 concurrent transactions, for example? So the relayer needs to protect themselves. So this is ideal for wallets or other systems that ensure that the user cannot send out duplicate transfers. But what you can actually get is basically the user already having funds on the destination side before their funds are locked up on the source side. And with this, what you can achieve is actually theoretically the negative latency transfer. Because if you look on Etherscan, when you perform this operation, what you will see is that the destination side transfer for the user is at 1 o'clock, and the source transfer time is at 1:01. Right? And if you compute the delta, that's a 1 minute delta in between the two. If you basically combine this like really deeply with like pre-confirmations, block building pipelines, like a really sophisticated off-chain actor, you can actually create like insanely high performance systems. Like systems that to a user, like not only do they not know that they're bridging, but they really like don't observe any latency at all. Like they submit it and 200 milliseconds the funds are available. And so you can just take away that whole bridge UX if you build it this way. And I think this is especially exciting for, let's say, neobanks, for example, or exchanges, because they really control the user wallet, right? Like they have off-chain infra that ensures that a user cannot withdraw twice. So they have much better control to ensure that indeed the source transaction will land on a chain itself. Pre-confirmations, they allow you to ensure that like the chain doesn't reorg. So you basically get like a signed certificate from the validators or from Flashbots or from some other party saying we will ensure this transaction gets into a block. And that way you know indeed like the funds will get locked up. So to me, when we actually thought of this, it became clear that this kind of gives you a protocol that almost has it all, because it fulfills like core protocol needs. It's at its core still very decentralized, even though like we use intent-based bridging, there's no risk to the end user, there's no risk to the smart contracts. There's technically like a slight risk to solvers for reorgs and such, but they can protect themselves against that. But there's no risk for solvers getting their funds back. They don't rely on an optimistic oracle, they still rely on the ZK pathway. And we serve user needs, because with this you can build like extremely fast protocols on top of Union. You can really, like if you have a good engineering team, you can really push this to the absolute limit and do those like sub-second transfers. So we'll be working on that, but we have a few teams that are also, I think, looking to be the first to do sub-second transfers. So this stuff just really excites me, to see this actually come to fruition. And comparing this, to be honest, to protocols where you still need to wait 20 minutes to have your transfer be completed, to me just shows that Union indeed has it all. So yeah, ZKGM. This is stuff we work on internally. This is stuff that excites me. This is actually going live on testnet 9. Probably in a week and a half. So the full intent-based APIs, etc., are all completed. The same for the content-based addressing. We've managed to squeeze that all in between 2 releases. All right, thank you.